Chilloquium. And this meeting is being recorded. And I'm so happy to virtually meet you all. My name is Soonwon. And as Anna introduced, maybe I might be the youngest faculty that might give this kind of colloquium, because I was appointed to MIT as an assistant professor just 2 days ago. So I'm a 2-day-old faculty. So I don't feel like I'm a professor. So I'm more like a postdoc in mental status. In other words, maybe I'm closest to you among the existing professors to date. Anyway, so my affiliation is MIT, but I have to say, I still feel like I'm a postdoc at UC Berkeley, and I'm still sitting in one of the offices at UC Berkeley because I spent my last 3 years here. Originally, I wanted to talk about the dynamics of quantum entanglement, which is what I worked on throughout my postdoc period. However, after talking to one of the organizers, I decided to change the topic, and my majority, maybe about half of it, is going to be a little bit of more personal side of talking about why I'm doing what I'm doing now. And I'm talking about a couple of turning points and a few people that I met throughout my journey. So please stop me whenever you have any questions. I think it's meant to be a conversational talk rather than a one-way talk. So let's get started. A little bit of bio. I was born in South Korea, it's a Far East Asia, indicated here. And if you zoom in, South Korea looks like this. And maybe the most popular city is Seoul. I was born in Seoul. However, after 12 years living in Seoul, during my elementary school years, I moved to a city called Daejeon. And Daejeon is a city in South Korea that's known for science and engineering. And then I graduated my middle school and high school before I moved to US for my college education. So how did I start studying physics? Until I became a middle school student, I studied middle school student. I didn't do anything particular that's related to physics. And I looked like this in my middle school. At that point, I was of course interested in math and science in general. However, there's nothing particular. But one day I was watching this TV, and on the TV, there was this documentary about the science high school. So I think it's one of the magnet school in Korea where the students are taught more specialized curriculum focused on math and science. And I really like this documentary, the notion of students forming a group and designing their own experiment and carrying out the experiment and doing research as a high school students and autonomous, like they are not passively learning something, but they are more actively engaging themselves to build something and invent something. And those concepts was fascinating to me. So I showed some interest about entering one of these specialized high school. At that moment, my mom took the opportunity and she was so happy that I'm about to, I'm enjoying this, and they made a deal. Hey, Soonwon, that's so nice idea. So actually, if you get into one of the science high schools, she promised that she's gonna buy a laptop for me. And I'm not sure how much, this was influential, but I was very passionate about entering the science high school. And I looked into the ways to get the admission. And obviously one of the best way is going on a local science or math competition and win some awards, prize. So that's what I did. So I studied pretty hard. At that time, it was my middle school year, so it was like a science competition rather than a physics Olympiad. So I did it, and I was pretty successful, and eventually I could get into the science high school. So I got into the Daejeon Science High School because there was a local magnet school there. I continued to study physics. Now, like studying from high school years in Korea, now they can choose like a more specific subject within science. So I chose like physics over chemistry or earth science or biology because I like the mathematical aspect more. But I have to say it was almost just the inertia that I the reason that I continue studying physics was because of the inertia. Like I've been doing physics over my middle schools. I enjoyed it definitely. I was pretty good at that. And I like the competition. Eventually, I was pretty successful. So I was lucky enough to be selected as one of the national delegates, and then went to the International Physics Olympiad. It was unfortunate that the Physics Olympiad was held in Korea, so I didn't go any international Olympiad, but still it was a nice experience. But I have to say this, going to the Physics Olympiad was one of the things that changed my life, because there I met many international students studying physics, and also even friends within Korea. Like I learned that they are thinking about studying abroad in the United States, for example, to develop their career in science or career in physics. So I just followed their route, and eventually ended up like moving to the United States to get my undergraduate education and Caltech. And that's how I came to the United States. Once I moved to Caltech, you know, as maybe you guys know very well, that Caltech has a lot of homework sets and a lot of problem sets, and people are chased by different, you know, problem sets. But I had this like one particular homework set or like one particular problem that I had to answer throughout the entire my college education. That was whether or not I should continue studying physics. So I have to say, up until my college year, one of the major motivation behind studying physics is because I enjoyed it and I liked solving problems. I definitely enjoyed getting a prize or winning the gold medal and getting fame for that as a student. And also sometimes my mom gives me like gifts like a laptop. But you know, now it's a different level. Like, should I continue studying physics for the rest of my life? But like, I cannot just do that because of I want to get another laptop from my mom. And this problem actually involved many sub-problems. For example, I had to ask myself, do I really love physics? Can I say that? And also, okay, at some point, I'll be no longer a student, but I'll be like a researcher. And then doing physics is like a job. And can I enjoy it? Can I enjoy it? And also, it's not studying physics, it's going to be doing research in physics. And I presume that there must be a big difference between studying and doing research. Also, if I continue studying physics, what does it mean? Does it mean I'm staying in academic, I'm following the academic career and is going to be a good fit for me? And also, is this plan realistic? So, and more pragmatically, like, can I do it? Like, what if I just, you know, cannot continue my study? Like, so what if I fail my grade and so on? And this set of questions was actually bothering me throughout the entire year, mainly because, you know, I didn't study physics because I was like, you know, destined or like determined to do it up until this point. And I have to say, I couldn't answer this question in the end. So this still remains as one of the open questions for me. However, when I was struggling to answer this question, there was one particular occasion, which is I took one of the class from electrical engineering and computer science, Professor Michelle Afros. She's not a physicist, and I took a course from her about information theory. But this was so fascinating to me. So what I learned in her class was how to represent information, how to quantify the amount of information, and how to store information or transmit or compress or decompress or encode or decode, or what it means by learning, like machine learning. So very elementary course. However, this was so it was so interesting to me because previous to this course, I thought the notion of information is something very abstract. But she taught us how to quantify and how to kind of manipulate the notion of this, you know, like abstract concept into something more concrete, something that you can do calculation for. And after taking course, it was very clear then, at least for the next few years, I'm going to study this information science more deeply. But at the same time, I did not want to do this study as an engineering study. I wanted to do it as a science, especially as a law of nature. I understood that this world and universe is governed by the quantum mechanics. So I decided to study this information science or science information from the perspective of physics. that's how I got interested in quantum information science. And around that same time, I also got the partial answer to my biggest homework problem. And that was, unless I actually try out, I can never know whether I'll be a good fit or not for the academic career. So what I ended up deciding was, okay, let's do quantum information science. It's not clear I can do this for my rest of my life or not, but let's at least try it out. And there was a reason that I I went to and I talked to like Professor John Pascal, and John was one of the most famous physicists and working on quantum information and quantum computations at my undergraduate institute. So I talked to him. Maybe I don't remember exact phrasing, but I talked to him basically in the following way. Hey, dear Professor Pascal, actually, I don't know what I'm saying, but I just recently learned about information theory and it's so fascinating, but it's not physics. I want to do something in between information science and physics. So could you tell me some guidance? Maybe it's confusing because I don't specify, anything. Like, could you just tell me, how can I learn more about information science? So I was very kind of honest and straightforward that I'm interested in information theory and asked for help. And he generously allowed me to do my undergraduate research over summer. And that summer I worked on, actually not so related to quantum information theory, but maybe still tangentially related, a topic of like purification of photonic states via linear optics with Nate Lindner. He was a postdoc at the time. He's now a professor at Technion. And then there was, I really enjoyed working on this research. But maybe more important thing is not just doing the summer research with Professor Pascal and Nate, but it's more important to, for me, it was more important to be able to talk to people in John Pascal's group. For example, I'd like to introduce two people, Liang Jiang and Alexei Gorshkov. Both of them were postdoc in John Pascal's group. And I enjoyed talking to them. Previously, I thought the notion of information is so abstract and even quantifying is very mathematical. But somehow those two people, like Liang and Alexei, managed to explain everything in a so physicsy way. So they explained some mathematical concept in a very intuitive way. And I was very fascinated about them. And one of the best memory that I had at Caltech was like being able to talk to all those postdocs and professors and learn about different aspects of physics from them. And then after talking to all these people, I decided that, okay, I want to pursue that direction a little further. Especially, I want to do something between an abstract theory and the actual experiment that we can carry out. So, and then I again asked for the guidance. Okay, I want to do somewhere between theory and experiment, and what should I do? And then John actually recommended me to go to do my PhD program at Harvard with the Professor Michel Lukin. And that's how I started my PhD program at Harvard, under the guidance of Michel Lukin. Throughout my PhD program, I more or less did what I wanted to, wanted to do, like this intersection of theory and experiment. And more specifically, I worked on multiple topics that is spread over 3 different fields. One is called the AMO physics. This field is a field where we talk about the individual atoms or molecules or using lasers to control the individual degrees of freedom. So the key subject or keyword of this field is quantum mechanics. Like everything is quantum mechanicals. And the second field is the condensed matter physics, where the focus is about the many-body nature. If you have a collection of particles, and the number of particles is very large, like Avogadro numbers of particles. How can we still describe the physical phenomena occurring from inside? What if now we add a quantum mechanical effect among those particles? And then study of this many-body physics is now often called the condensed matter physics. And third branch is like quantum information science. Okay, using quantum mechanical principle or quantum mechanical object, can we build a new type of sensors or simulators or even computers? So I had to learn a little bit of all 3 fields, and that was definitely tough. And also, while I said I wanted to do somewhere between the theory and experiment, I have to confess that it was not so easy because I didn't really know what I meant when I said that. So I have to say the beginning of first few years of my PhD was not as smooth as I thought. But nevertheless, I just stick to the field and ended up working on multiple topics, so I can give you some sense about what I worked on. One example is somewhere in between AMO and quantum information science. So one topic was how to use a single atom in order to build a quantum computer. Another topic that I worked on is so-called the quantum convolutional neural network. Here we asked how to utilize some of the theory topics that's popular in condensed matter, so-called the renormalization group flow, in order to design a quantum algorithm. And maybe another topic at the intersection of AMO and condensed matter is building a quantum simulator. And I'm going to elaborate on this, but the spoiler is that eventually we utilize what we call the black diamond as a quantum simulator in order to see many different interesting quantum phenomena that occurs in out of equilibrium. So I'm going to talk about the black diamond experiment over the next couple of slides. By the way, do you have any questions so far?
What do you mean by a convolutional neutral network?
Oh, did I say neutral network? Sorry, like it's a typo. So it should have been the neural network.
That's what I thought.
That's right. Yeah, that's right.
Thank
That's
you.
my typo. All right, thank you. Okay, let's talk about this black diamond experiment a little bit. So this black diamond looks black because it contains so many defects that's called the nitrogen vacancy color center. So it sounds scary, but actually conceptually it's a very simple object. So we all know the diamond is just the carbon atoms arranged in a so-called diamond lattice structure. And suppose you kick out two nearby carbon atoms and substitute one of them with a nitrogen atom and leave the other one as a vacancy. And if you have this particular nitrogen vacancy pair inside the diamond, it traps extra electron and forms essentially a molecule. And we can calculate the quantum mechanical energy level of the molecules. And luckily enough, those energy levels are lying in between the band gap of the diamond. And using the laser excitations and microwave excitations, we can manipulate the quantum mechanical state of those artificial atoms. So namely using the green laser excitations, we can read off the quantum mechanical state of the defect. And also we can prepare a certain quantum mechanical state by just illuminating the green laser. What happens is if you eliminate green lasers, you get excited and this excited state emits some red fluorescent light and then come back to a particular quantum state in the ground state manifold. And we can apply the coherent microwave in order to manipulate the different quantum states of these sensors. Because of this nice property, single NV sensor has been already utilized in order to do quantum information processing or sensing or as a quantum memory. So in short, this nitrogen vacancy color center is like an artificial atom. However, unlike the real atom, it's already trapped in the diamond. So you don't have to hold the atom, but just naturally there. And we can, because now it's stationary, we can use our laser light or the microwave to manipulate and then utilize their quantum mechanical effect. So conceptually, we can think of it as a single atom or maybe a single spin 1/2 particle with an approximation. So system we had is slightly different from the conventional settings. We had this so-called black diamond. So this is a picture of a diamond. Actually, this picture is taken by my iPhone when I was a graduate student. And it literally looks black because it contains so many NV centers inside. So it absorbs energy, absorbs the light, and that's why it's not transparent. At the abstract level, you can think of this black diamond as an ensemble of these spin 1/2 particles that are close enough. So their average distance is about 6 nanometer. And at that length scale, these spins or the atoms are interacting by the dipole-dipole interaction. So at the abstract level, yes?
Question, the 6 nanometers average distance, is that something that you created or is that just part of how the system is set up?
Yeah, that's right. So we fabricated this black diamond. Actually, we didn't do it. Actually, a group of Japanese people did it. And then we had to figure out the density. So it's not engineered, but something that we had to figure out.
I see. Thank you.
All right. So, so in short, we have this system where it's highly disordered in a sense that the location of this MV center is random because we did not engineer. And also it not only have an MV center, but also contains other types of defects. And they are strongly interacting by dipole-dipole interactions, and they are located in the semi-dimensional way. And the key question is, okay, we got this like very curious diamond sample. What can we do with this? Can we do anything useful? And that was my essentially the PhD project. So this is an actual experimental setup. So we have the circuit that delivers a microwave line, and this is the sample, our black diamond. And if you illuminate green laser, what happens is, as I said, they are emitting the red fluorescent light, and this is actual picture, a little bit enhanced for the color scheme for the red part. But you can actually see the red light from this. And we are preparing a certain quantum state. In actual, our science experiment, we didn't do the experiment with this bulky diamond sample, but we fabricated a smaller beam of diamond because that's easier to manipulate with the microwave. But anyway, so what can we do with these samples? Turns out we can do many interesting stuff in the field of quantum information science. One of the first progress we made is Hamiltonian engineering. So we realized that by using microwave controls, we can modify the Hamiltonian or the types of interaction between spins from dipolar interaction to something that we desired. And this is the basis of the idea of quantum simulation. We are given a quantum mechanical system. How can we use it to simulate some other system? And using this Hamiltonian engineering technique, we did a bunch of experiments, and one of them is quantum thermalization experiment. Suppose we consider the ensemble of spins, where the half of the spins is polarized to the one direction, say up direction, and the other half of the spin is polarized to the opposite directions, and let them interact one another quantum mechanically and study how they eventually thermalizes to a random orientations. So intuitively, you can think of it as like mixing hot water and warm water. We believe that once they are interacting one another, they reaches equilibrium. And we are studying how those equilibrium process or the thermalization process occurs in this quantum mechanical system. And we show that this thermalization speed can be actually controlled if you have a strong disorder. And also using the similar technique, we could prove exotic phase of matter. For example, at that time, a new theoretical prediction predicted that it is possible to engineer so-called a discrete time crystal where time translation symmetry is spontaneously broken. And it's known that this kind of exotic phenomena could only occur in a system that does not thermalize or thermalize very slowly. And utilizing the fact that our thermalization speed can be suppressed by disorder, we could also see the signature of discrete time crystalline order. Finally, we also use this ensemble of MV centers as a small sensor, such a way that we can detect the oscillating magnetic field. And turns out by utilizing high density of this ensemble and our Hamiltonian engineering, we could achieve the world's best AC magnetic field sensitivity normalized by volume of the sample. So not only those set of experiments, I was lucky enough to do other types of experiments, other types of research.
May I ask a question about the previous slide?
Sure.
Oh yeah, thank you so much. So I have a question about the quantum thermalization. So the thermalized state itself seems to be like kind of disordered state. So I just wondered about how the strong disorder can like suppress the thermalization process.
Oh, I see. So yeah, I wasn't very clear about what I mean by disorder. And the term disorder is used in two different ways in the community. In condensed matter community, sometimes disorder, not necessarily condensed matter community, sometimes people say disorder to describe the state. Like spins are randomly oriented, so that's a disorder state. But sometimes people use disorder for the different meanings. For example, the spins, the location of spin is randomly located, but that's different from the polarization is random, the spin orientation is randomly located. So while we say the strong disorder in this context, I'm talking about like I say, the position of the spin is random, or at the same time, individual spins has their local environment, which look different for every spin. In that case, we also say the potential disorder. And those are the types of disorder that I'm talking about here. And yeah, that disorder slows down the process where the polarization of spins becomes disordered. So it's a different notion of disorder. So I hope it was clear now.
Thank you so much.
Oh, Professor Choi, I can also follow up with a question on that. So when I hear about, and I'm ignorant of quantum thermalization as the notion of quantum thermalization in general, but when I hear about thermalization, like in statistical mechanics, it's straightforward, where you sort of collisions with molecules and so on can induce this sort of stable equilibrium state. In the nitrogen vacancy system, however, what sort of physical mechanism mediates the interactions between the molecules? Because I don't imagine it's similar to as in statistical mechanics, where you get to this steady state equilibrium, but it's some sort of quantum mechanical interaction.
Yeah, that's right. So here, these MV centers are stationary and they are not moving, so they are not colliding. However, they have a spin degrees of freedom, which could do the flip-flop. So when I by thermalization is that you can think of it as tiny dipoles, the tiny magnets. And these magnets are like exchanging their magnetization to one another. So if you have an ensemble of spins that's half up and half down, they start to exchange their magnetization such a way that their distribution becomes random. And after a long time, like all spins will be randomly up and down, as opposed to half up and half down. Did I answer your question?
Yeah, I think that makes sense. Yeah, thank you.
Yeah. By the way, yes, go ahead.
So I kind of got excited. How do you manipulate thermalization rate with disorder? What is the mechanism for this? Do you make it more disordered? What changes?
That's right. So I did not explain how we control disorder. So in this case, the location of spin is fixed. So the disorder associated with the location is something that we cannot control. However, individual spin experience a different local magnetic field. And that's also like a disorder. It's a random number. Every spin experiences a random on-site field. But what we did was using Hamiltonian engineering, we manipulate so that this disorder goes away. And have you heard about like a spin echo? So the idea is very simple. Like if you flip the spin like periodically up and down, and your local magnetic field, it becomes on average 0. That means no matter what the values are, they all become 0. That means it's homogeneous. So we didn't do exactly spin echo because we wanted to control the type of the interaction as well. However, the basic, the working principle is the same. We did the Hamiltonian engineering in such a way that on-site disorder becomes suppressed. And then so that the suppressed disorder will facilitate the thermalization process.
So you're saying you will apply an external pulses to essentially control the strength of disorder, right?
Exactly.
But the question is, what is then, okay, that's good that you don't need to prepare many samples, you just use one, right?
That's right.
But then still, what makes it, why relaxation depends on disorder strength?
I see. That's an excellent question. So if you have a multiple spins, the mechanism of thermalization is they are exchanging their polarization. But if you have a disorder, maybe this field, one spin and the other spin may experience a different local magnetic field, such a way that if you exchange the the polarization, and then the initial and the final state might have a slightly different energy. And due to energy conservation, this process will be prohibited up to quantum mechanical uncertainty principle. So if you don't have a disorder, every spin experiences exactly the same field. The up, down, and down, up has exactly the same energy. So this process becomes resonant and energetically resonant process. Therefore, this will happen at a more effectively faster rate.
I see. I'm sorry, is it related somehow to Anderson localization? It's kind of...
Definitely. So the large motivation behind this one is to study how the Anderson localization is generalized to the many-body interacting case.
I see. That's amazing. Yeah, thank you. I'll read more.
Great. By the way, how am I doing with my time? Actually, I'm only halfway through. Is it okay?
Yeah, time is fine, I think.
All right, good. So
Professor,
that's,
Professor Choi, if I may interrupt, I have one more question.
Yeah.
So in one of your previous slides, you had this kind of optical pumping scheme where you excited the nitrogen vacancies into an electrically excited state, and then it would kind of decay into the back to the ground state, and that would create
That's
the
right.
red fluorescence.
that's right.
So a couple of questions on that. Are you concerned about the lifetime of the excited state when you're considering these Hamiltonian engineering projects?
What am I concerned about?
Like I imagine if the lifetime of the excited state is extremely short, then it might be difficult to observe some of these effects, like quantum thermalization, for example.
I see. Good question. So here's a level scheme. So we have the electronic ground state and electronic excited state, and we can do the optical pumping. However, if you zoom in, this ground state is actually made of the 3 different spin states, depending on their magnetic moment orientations, +1, 0, -1. So what we did is we used this optical pumping in order to prepare a particular a spin state in the ground state manifold. However, our thermalization physics is studied within the ground state manifold without exciting to the excited state. So the lifetime of the excited state is not relevant for the physics that we discussed. And the lifetime or the coherence time within this ground state manifold is relevant one. But in fact, those lifetime is determined by the strong interaction, which means it's not the external noise, but it's more like an internal one.
Thank you. Okay, that makes sense. So a short excited state lifetime is actually beneficial because you can just pump into the excited state and it decays almost immediately to the ground state, and you scramble the
You can
spin
say
state.
that. You can, yeah, that's right. That's
Okay.
right. It shortens our preparation time.
Thank you.
Okay, great. It's great that we have like this kind of lots of questions. Okay, any other questions? So yeah, so not only this black diamond experiment, I was lucky enough to be exposed to many other topics centered around those 3 fields. So I worked on so-called the Rydberg EIT polarity problems, how to make photons interact one another, or many-body localizations. I think there was a question about that. Or how to engineer a driven dissipated dynamics, and how to engineer a quantum computer out of single photon, the single atom as I described, or how to use the Rydberg atom array, a newly realized experimental platforms in order to figure out different phases of matter. And also I studied a novel type of non-equilibrium phenomena called quantum many-body scars. If you have any question about those, I'll be happy to answer in details, but maybe after my second part. So that concludes my research at Harvard. And after this work, I moved to UC Berkeley to do my postdoc period. But starting from my postdoc, I wanted to go back to my original motivations. So remember, like the reason I joined Harvard was because I was asking for the advice from John Preskill. Hey, I want to do somewhere between theory and experiment. And then he recommended me to go to Harvard, and then it was fantastic. I actually did something that's intersection of theory and experiment. But after that, I was feeling like, okay, actually, I want to do a little more theory now, because I originally wanted to study the information theory in connection with the quantum mechanics. So during my postdoc years, I decided to do a little more theoretical topic. And that's what I'm going to talk about for my second half of the talk. And that's the dynamics of quantum entanglement. So any questions so far up to this point? So I'm going to change the topic a little bit and talk about the research project that I have done recently. Okay, if not,
I have,
sure, yeah.
Oh, so after finishing your PhD degree at Harvard, did you kind of like consider that you like theory more than the experiment, or you just like wanted to learn more about theory at this moment? Or
Yeah,
I just wondered that your internal motivation.
That's right. Yeah. So after working on like kind of intersection, I started liking experiment even more. So the reason I wanted to do a little more theory after my postdoc was for my own training, rather than I wanted to do more theory. So I felt like I need to work on more serious, like an abstract and mathematical, the theory project, so that I can come back to the this intersection with a new set of tool sets that I'm familiar with.
Oh, thanks.
Okay, great.
Could you
So-
clarify a little bit more about what you mean by the intersection between theory and experiment? So did that consist of like you maybe performing the calculations for your experiment instead of like working with a theorist, or like what exactly did that consist of?
That's a good question. So like, that's partly true. Say, I do calculations to assist the experimentalist. And also if experimentalists get data, I suggest how to process the data analysis. However, that's only the part of it. I think that what I mean by the intersection is mostly about choosing the research topic. So as time goes, eventually, it's not about carrying out some technical calculation, but it's about how to ask questions. What questions do you ask in order to do research? And what I mean by intersection is my research questions are theoretical questions. However, it's highly motivated by the experimental considerations. For example, people could consider, okay, if you have a universal quantum computer, what can we do? And that's a well-defined question. It's a very meaningful question. However, I would like to ask the slightly different question. Okay, we have these experimental platforms, like say trapped ions or like superconducting qubits and the Rydberg atom arrays existing in the laboratory already. And they have a pros and cons. They have a coherence time of this length, and they have this capability. However, a certain manipulation is easy, but some other manipulations are much harder. And given this capability, can we still do something useful that can make an impact in today's technology, rather than assuming we have a universal quantum computer? So and that's the type of question that I'll enjoy more. So from that point of view, I had to know, what's existing, what the capability of the existing technologies are. And of course, for that, I need to have a conversation with them. And also I propose new experimental protocols. Hey, turns out if you do these manipulations, even with this limited capability, you can do these and that exciting topics that theorists are interested in. And this close conversation is what I mean by the intersection. Did I answer your question?
Yeah, thank you so much.
Mm-hmm.
But do you consider doing experiments and theory at the same time? Is it possible?
Many people do that, especially in this quantum information science field. There are many faculty members who do both experiment and theory. Myself, I don't do experiment by myself, but I enjoy collaborating, because doing the experiment is a lot of commitment. But I prefer actually flexibility. I want to talk to multiple different experimental platforms, so that and then have I want to enjoy this flexibility. But once you do the experiment, often that's very difficult because you need to dedicate to one or few platforms.
Mm-hmm. Thanks.
All right, then let's get started with the second part. So the dynamics of quantum entanglement. So entanglement is a very interesting phenomena that occurs in quantum mechanics, and maybe this is the most unique phenomena in quantum mechanics. And in short, the entanglement can be described in the following way. If you have a multi-body system, say some quantum system that can be divided into two parts, A and B, interestingly, it is possible that globally you have a zero entropy. So the entropy of the total system is zero. However, the entropy of the subsystem is larger, non-zero is larger than zero. And that's very curious because this kind of phenomena cannot happen in classical mechanics. And this could happen in quantum mechanics because some types of information can be shared between A and B. So let's recap a little bit about how to think about entanglement with an example. Let's consider two spin-1/2 particles or qubit, where each particle could be in a state 0 or 1, or up and down equivalently. And we know that quantum mechanically there are 4 distinct states we can consider, 0, 0, 0, 1, 1, 0, 1, 1. And in fact, any linear combination of those 4 configurations is valid quantum mechanical state. So there's a very curious, interesting quantum mechanical state, so-called the Bell state, which is a linear combination of 0, 0, and 1, 1. And this state is still called a pure state All these states, 0, 0, 0, 1, 1, 0, 1, 1, all pure state, and they do not have entropy. The reason being, we can always apply a reversible unitary transformations from one another. So this Bell state, if you apply certain unitary, you can transform it to 0, 0, and from 0, 0, you can prepare this Bell state. So there's no increase of entropy, therefore even this Bell state is considered a pure state that does not have any entropy. However, if you look at the only one particle of the two particle system in Bell state, now this particle is not in a superposition, but in a mixture of 0 and 1. With the probability 50-50, it is in a state 0 and state 1. And without applying unitary to the whole system, just applying unitary acting on a single particle, it is not possible to make this particle in a definite quantum state, say 0 state or 1 state. Therefore, fundamentally, if you do not have access to the other particles, this subsystem belongs to a so-called mixed state that's associated with a non-zero amount of entropy. And whenever this happens, we say these two particles are entangled with one another. And what's happening is certain amount of information is shared between and delocalized between the two particles. So unless you have access to both, you can never retrieve those informations. And this loss of effective information due to locality is essentially the gist of entanglement. And this quantum entanglement plays a central role in many different areas. For applications, we now know that the entanglement is a necessary ingredient in order to do quantum computation. And now in condensed matter, people consider different phases of matter based on their underlying entanglement structure. And in order to build a quantum communication or establish secure security protocol, or do some high sensitivity quantum sensing protocol, the entanglement is a central object. More on the basic science level, this entanglement is also very important. We talk about the statistical mechanics and the second law of thermodynamics, saying the closed system has a non-decreasing amount of entropy. In fact, if you want to combine this statistical physics together with the pure quantum mechanical descriptions, this entanglement plays a central role, and it's responsible for the growth of entropy in the generic thermalizing system. And interestingly, this aspect has been already experimentally studied in one of the very nice experiments done at Harvard. So with that, I think it's clear that how the entanglement changes over time is an important question. For example, suppose we have initially unentangled quantum states, n particles all in a certain, n qubits all in 0 state, and it undergoes a certain unitary evolution. And we can ask how its subsystem A is entangled with the rest of the system. So how this entanglement entropy changes as a function of time. The entanglement entropy is an entropy generated by not knowing the complement of the system. Interestingly, this question is notoriously hard and nobody knows the answer to date. However, under certain conditions, we can use some mathematical, you can consider a mathematical toy model to analyze this problem. So this one of the toy model is called the random unitary circuit. So instead of considering a generic unitary, we consider the following particular quantum dynamics. We again start from all qubits in 0 state. We apply 2 qubit unitary. However, the 2 qubit unitary, which is basically 4x4 matrix, randomly choosing the unitary group. And you apply this each unitary group to the nearest neighbor qubit. So this each blue box is an independent 4x4 unitary gate applied to corresponding qubit. And you do it in layer by layer and then generate the evolution. And this random unitary gate turns out mathematically solvable using the statistical properties of random unitaries. And also, other than unitarity and the locality, like the space-time geometry of this diagram, there's no other features assumed. Therefore, in some sense, this dynamics represents the most generic unitary evolutions that you can consider. And this model has been already utilized for the many different purposes, studying operator spreading or quantum chaos, including entanglement growth, and then also recently about to study the hydrodynamics. For these models, people realize that this entanglement entropy generally grows linearly over time until it saturates to the maximum value set by the size of the Hilbert space for the subsystem A. And so that's the maximum entanglement that you can achieve. But natural question is, okay, is this really true in reality? In realistic system, nothing is perfectly unitary. Whenever you have a quantum mechanical system, it's always coupled to the path. So what happens is the unitary dynamics within the system will try to generate entanglement so that the entropy of the subsystem increases. However, generally they are also coupled to the path, and some of the information leaks to the environment, and that leads to much more richer dynamics.
Soonwon,
So yep.
can I ask a question about the previous slide?
Yeah.
So here you said you're randomly sampling from the unitary group. I've also seen random sampling from the Clifford group. So to what extent can the Clifford group reproduce some properties of this random circuit when you sample from the unitary group?
Good, good. The Clifford group is a subset of the unitary group. It's a particular subset such a way that if you only use a Clifford group, you can classically simulate these dynamics easily. So there's a classical smart algorithms where it allows you to simulate the quantum dynamics even for relatively large system sizes. That's why people use a Clifford group. Because it's a subset of the unitary group, there's a similarity and the distinctions. And now we are treating this unitary as a random variable because it's randomly drawn from a certain group. And we can talk about their statistical properties, say mean and variance, or more mathematically, the first moment and the second moment and higher moments. The Clifford group and the unitary groups have an identical first, second, and third moment. However, starting from the fourth moment, their statistical properties are different. So, so many of the features I'm talking about, some aspect is sufficient to have like the same, second moment or third moment. But in general, it's statistically distinct because the Clifford group and unitary groups are statistically different because it differs by higher moments.
I have one more follow-up question. So, so the Clifford group performs a 3 design, so you can go to this third moment of the hard measure.
That's
but
right.
Is there any work being done on trying to find these 4 or 5 designs?
Existence of 4 and 5 designs are proven. So maybe the question is there any particular ensemble that forms a 4 design but not 5 design, or like 5 design but not 6 design? And those questions, I don't know the answer. And it could be known that it's simply that I don't know.
All right, thank you.
Great. Okay, and recently there's been a paper saying actually if you there could be a phase transition in the dynamics of entanglement. So it was a very interesting work. So let's go through their argument slowly. So they generally consider this random unitary circuit. Layer by layer, they apply this random unitary gates. But in addition to the unitary gates, they also introduced a random measurement with the probability P. Each qubit will be projectively measured or not. But in case it's measured, you collapse the wave function so that this measured qubit will collapse its quantum state to either 0 or 1 according to the certain measurement outcome probabilities, like following the Born rule. And we continue this process. And then you will lead to many different measurement outcomes, 0 and 1s. And then eventually you will get a total wave function after a sufficiently long time. And now for that wave function, we consider the entanglement entropy between the 2 parts A and the rest B. Specifically, we consider the, trace out the B part and get the reduced density matrix of A and calculate the von Neumann entropy to calculate the entanglement entropy and average over different choices of unitaries and different measurement outcomes. And they argue that if you compute this average entanglement entropy, there exists a phase transition. If you perform measurement sufficiently frequent enough, the entanglement entropy cannot grow too much. So this entanglement entropy remains a small value, even if your system size is very large. This small value is independent of the system size. But if measurement rate is sufficiently small, smaller than a certain threshold, the entanglement still grows and grows indefinitely until it saturates to the maximum value that you allow to the system, proportional to the size of the quantum system, the total system. And they say they call this is the critical phenomena that have similar to the critical phenomena in the many-body system. and it's called adoptive entanglement phase transition. And they prove both the numerical and analytical argument of how this entanglement phase transition could happen. But very interestingly, when this paper appeared on the archive in 2018, basically the next day, there was another paper saying, in fact, this entanglement phase transition is not possible. And turns out their argument was not 100% correct. However, they proposed very interesting question, and I wanted to go over that. They argued in the following way. So let's consider how entanglement changes over time. Every time step, you could have an increase in entanglement due to the unitary operations and decrease in entanglement due to the measurement procedure. However, these two terms have a different scaling behavior. So if you want to increase entanglement between the two subsystem A and B, you can only, entanglement is a form of correlation. So correlation could only be generated if you have a unitary that act across the two parts. So it only happens by the unitary acting on the boundary between the two parts A and B. So the growth rate is limited. However, the measurement is different. At every time step, we are measuring each qubit with a certain probability. In other words, if you consider the macroscopic system, you measure the macroscopic number of, you perform macroscopic number of measurements proportional to the size of the system and the probability of measurements. And those measured qubits will collapse its wave function to either 0 and 1. And once it collapses, it completely disentangled from the rest of the wave function. Therefore, the decrease in the measurement could be as large as something that's proportional to the size of the system. So if you have a two-term, in the steady state, the decrease is proportional to the volume, but the increase is only proportional to the boundary size. Therefore, always the negative term wins, and then you cannot have entanglement entropy unless the steady state entanglement is already 0. And that was the argument behind the absence of the volume entangled phase. You can only have a small amount of entanglement. And initially people got puzzled. Okay, this explanation seems right. Then what's going on? Like what is the first paper, and then what is our numerical evidence? So one of the first projects that I did as a postdoc at UC Berkeley was actually answering this question. And we did, and that's why this paper ended up not correct. And then we answered this using the notion of quantum teleportation. So let's review quantum teleportation briefly. So suppose we have two people, Alice and Bob, spatially separated, and Alice is holding a qubit in an unknown quantum state psi. And Alice wants to send this qubit to Bob. One way is to perform measurement and then send the measurement outcome. But that's not good, because once you perform measurement, you need to know which measurement basis to perform. And without knowing the quantum state, it could be that you just perform measurement and destroy the wave function without actually revealing what the quantum state it was. So you cannot perform measurement and then send the measurement outcome. That doesn't work. The other way is you physically bring this qubit to Bob and then hand it over, and that works, of course. However, there's limitations because we want to send it maybe as fast as possible. Turns out there's a smart way to transfer this quantum state if you have a shared Baire pair. Suppose Alice had another qubit that's entangled with the Bob in a certain Bell state, for example. And what you could do is you can apply locally, only within the Alice's part, some entangling interaction between the two qubits in A1 and A2, and then perform measurement on each qubit. And then you can design this entangling unitary and then measurement in a certain basis, such a way that after the measurement, these two qubits becomes in a certain disentangled state, so 0, 0, 0, 1, 1, 0, 1, 1, with certain probabilities. And the final state on Bob's side now suddenly becomes the quantum state that Alice had originally, up to local basis change that you knows how to handle if you know the measurement outcome from the Alice's part. So in this way, without having to physically bring the quantum state to Bob, you can actually transfer unknown quantum state. And this phenomenon is called quantum teleportation. And this quantum teleportation can be used not only to transfer the quantum state, but to transfer the entanglement itself. Suppose now Alice has an entangled pair between the A0 and A1. you can think of this A0 is actually far away from Alice. So the A0 is held by someone else, say Charlie. Now, what Alice wants to do is, Alice wants to dispute this entanglement by sending this A1 to Bob. Again, we can just physically bring it. However, there's a better way. The better way is the following. If they share an entangled pair, A2 and B, they repeat the same procedures, apply exactly the same entangling unitary, and perform measurements. And what happens is, after the measurement, those two measured qubits A1 and A2 are completely disentangled. However, now the entanglement between A0 and A1 is now changed to the entanglement between A0 and B. In this way, Alice successfully can transfer the entanglement with A0 into to Bob's qubit. And this is idea of like teleporting the quantum entanglement. But let's have a little bit of closer inspection. Suppose before applying unitary gate or before performing any measurement, we calculate entanglement entropy between Alice and Bob. At this point, Alice and Bob, and they are entangled because there's an entangled pair between A2 and B. And what we do is we perform some unitary and perform measurements. If you do not apply this unitary and just directly measure A2, you will destroy this entanglement between A2 and B because A2 will collapse its wave function. However, by applying a certain unitary and measurement, this entanglement with Bob is not destroyed, but rather relocated to the different entanglement. In this case, it's moved from A2 to A0. So that way, the measurement do not always destroy the entanglement. It just teleports the entanglement from one location to the other. And that's what we showed in this random unitary circuit. What we showed is when you consider this random unitary circuit and measurement, we can generally decompose the system into A and B. And this A and B shares many pairs of Bell states. And then we perform many measurements of some part of the system. What we showed that was as long as this unitary evolutions is sufficiently random and sufficiently scrambling and sufficiently entangling, generically what happens is this entanglement is not destroyed, but rather relocate to the rest of the systems, such a way the entanglement is not destroyed even if you perform many extensive measurements. And this way we could show that, together with the other more different types of analytical the theory analysis, we could show that this entanglement phase transition could still exist and lead to the sharp phase transition. The study of entanglement phase transition has become very popular past a few years. So I only talked about a particular aspect of this, but since then there came up with there has been many different interesting theory questions. For example, how to describe this phase transition more rigorously, and then we had to develop a new theoretical framework to describe. And turns out one of the nice way to describe this phase transition is by mapping this random unitary circuit into some classical statistical mechanics model. And turns out by analyzing the classical statistical mechanics models and their ordering, conventional finite temperature ordering phase transition, we could also understand this entanglement phase transition in the quantum circuit picture. And we have also started thinking about whether there exists other types of phases if there is not only the unitary measurement, but also some symmetry or long-range interactions. And also there are many other questions that needs to be resolved and answered, which are like, for example, how to probe them experimentally. And also this phenomena is interesting, but it'd be nice if you can build some practical applications out of this phenomena. And also it would be nice if you can answer some of the unsolved problem in other fields of physics by using some of the new technique that we developed for this work. So locally at UC Berkeley, there are many people already working on this related topic. Anna, Zach, and Max, and Imo. Anna is an undergraduate, and Zach, Max, and Imo are graduate students. And they belong to the group of Norman Yao and Ehud Altman. And I only listed UC Berkeley people here because that's who I collaborate with. But worldwide, there are now a large group of community focusing on this interesting new problem. Okay, that was the end of the last slide of my research part. So I wanted to conclude with my conclusion slide. On one side, I wanted to emphasize that the modern research is highly interdisciplinary. For my case, I talked about the intersection of theory and experiment, an intersection of 3 different branches of physics. But not only me, but I have to say that many of the modern research topics becomes increasingly more interdisciplinary. So that would be, I think, one nice take-home message. At the same time, I wanted to mention that pursuing academic career involves a lot of talking to a lot of people and a lot of mentors. So I talked about my mom, and of course my mom represents my family, and different professors from my undergraduate or graduate schools or even in postdoc years. I'd like to say that building my academic career as a physicist, I was highly influenced by all of those peoples. So if any of you are also interested in pursuing an academic career, I highly recommend talking to as many people as possible. So with that, let me finish my presentation. Thank you.
Thank you so much, Professor Choi. We're a little bit over time. I'm sure we have, I don't know if you have time to stay a little bit longer, Professor, but if there are maybe one question.
Yeah, I'm fine. Maybe for 15 more minutes.
Mm-hmm.
I had a question about the random unitary circuit. So are you kind of assuming a like nearest neighbor coupling with the way that only like 2 qubits are coupled at the same time next to each other?
That's right. In this particular model, yes, we are assuming only literally this geometry.
And with the projective measurements, is there a certain basis, or are you maybe like switching bases between the different measurements?
Yeah, it turns out because we are applying random unitary, so the basis doesn't matter because like different bases can be considered as a unitary transform to one another, which can be observed as a part of this unitary. So statistically, it doesn't matter. So we are usually assuming that the measurement basis is either 0 and 1 basis.
Right. And also, like, is there any kind of physical manifestation of this phase transition that we would expect in some physical system, maybe?
Excellent question. No, actually, I have to say, we haven't found any observable, any like peculiar dynamics in the observables that occurs under these phase transitions. But let me elaborate on this a little bit. So it's a kind of deeper question. So what do you mean by physical? For example, so here what we mean is there exists a phase transition in the entanglement entropy. And entanglement entropy is an information theoretic concept. You know, how entropic the system is if you don't know these parts, right? But is this entropy observable? It's a physical. To me, it's physical. Then we definitely have a physical observable. But I mean, let's go back to our quantum mech 101, where we talk about observables defined by expectation value of the Hermitian operators. And actually, we can show that it is impossible, or at least extremely difficult, to find a linear observable, Hermitian observable, that detects the phase transition. And that's because this phase transition is not a phase transition in the observable, but more like an information theoretic ones. So it's more like the change in the statistical behavior. And in fact, that's the one makes me very excited about this research topic, because it's totally, in some sense, extremely different from many of the phase transitions that we have studied in the condensed matter, where usually we talk about the phase transition in the observable quantity, but here it's like information theoretic quantity. So yeah, thank you for asking that question.
Thank you.
I have a follow-up question for that. So what is the kind of the order parameter for this entanglement phase transition in the case? Is it kind of like information like theoretical one, or is there some physical like order parameter in this phase transition?
That's right. I have to say it's an open question. So like many people actively seek after like quote unquote order parameter. We now understand we cannot have regular order parameter, and we need to use some kind of information theoretic order parameter. So there are definitely many quantities being considered, but that's like somewhat technical. But yeah, so I think it's fair to say there's no the answer for this order parameter. We are still like trying to understand how to how to what would be the good perspective to study this phase transition. But we generally believe it's the information theoretic type. So for example, so one example that we consider is so-called the Fisher information. The Fisher information is a concept that's popular in metrology. So it goes by in the following settings. So suppose you tune a certain parameters, and then change of these parameters will affect measurement outcome of a certain observables. So you measure a certain observable and it has a certain probability distribution. But if you change a certain parameter, then this probability distribution will change a little bit. And from this change in the probability distribution, how much information about the parameters can you retrieve from this measurement outcome? And we can try to quantify this amount of information encoding the measurement outcome, and that's the Fisher information. So we can apply this theory to this this random unitary circuit, and you can use this Fisher information as an effective order parameter of the system. It works in a somewhat in certain in some way, but it's not so it does not draw exact analogy to the conventional order parameter in the condensed matter systems. So there's some limitations.
In that case, like, what is the difference between the information theoretic type, like order parameter, and the like physical type order parameter? Is it related to the observable idea that you just mentioned before?
That's right. Yeah, yeah. Whether you use a Hermitian observables or not.
Oh, I have another question. So, Professor, now that you're going to be at MIT, do you plan on, ever incorporate or in the future incorporating more experiments to your research repertoire, or will you be continue to focus more on theory as at Berkeley?
Yeah. So, yeah, I'm starting my group at MIT. I'll continue to focus on theoretical part. So certainly, like I'm very, very interested in collaborating with the experimental team. So naturally, I'll talk to like tons of experimentalists at MIT and also at Harvard, but worldwide, I'm already collaborating with the experimental team at Caltech, for example, also teams in South Korea, for example. But yeah, so I have no immediate plan to do an experiment by myself.
Thank you so much. Yeah. Any other last questions we have? Okay, if not, thank you so much, Professor Choi, for a wonderful talk. And thank you all for coming today. We had an excellent turnout. Yeah, I think this was a great turnout for our first Chilloquium. And again, thank you, Professor Choi. I think everyone learned a lot. Next week, we will be having another Chilloquium. It'll be on Monday at 4:30 probably, but keep an eye out on your emails for when we give that announcement. So stay tuned. And again, thank you very much, Professor Choi. It was a wonderful talk.
Thank you.
Thank you.
Thank you. Bye-bye.